Hello, everyone. Welcome to the Vantage seminar. We're continuing our series of talks on rational points on higher genus curves and the Chabati method. And today we're very happy to have Sachi Hashimoto, who's speaking on rational points via p-adic L functions. So, Sachi, is it all right for us to record this talk?
Yeah,
Oh, great. And everyone, feel free to ask questions during the talk. Sachi, please go ahead.
great. Thanks so much, Rachel, and thanks, Rachel and Drew, for inviting me to give this talk. So I just wanted to start with like a series of problems about rational points, many of which you may have seen before, but I just think it's interesting the vast behavior that rational points can have, and it kind of tells us why it's so hard to describe the behavior of rational points and to completely determine rational points on higher genus curves in general. So um, the problem of finding rational points on curves dates back at least to Diophantus in the 3rd century AD, and this problem comes from the Arithmetica. So Diophantus tells us to find 3 squares, which when added give a square, and such that the first one is the side, so better known as the square root of the second, and the second is the side of the third. And so if we write this in algebra, we're asked to find x and y satisfying this equation here. And this is now known as the singular equation. So if we get rid of the singularity at 0, 0, we're finding rational points on this kind of nicer curve here. Diophantus actually gave a solution. He gave the solution 1/2 9/16. And if he had Desmos, then he might have plotted this curve here and its rational points. And in 1990, in his thesis, Wetherell showed that the complete set of solutions to this is 0 plus or minus 1, plus or minus 1/2, plus or minus 9/16, and plus or minus infinity. So if you sort of don't believe in the number 0 or negative numbers or infinity, then Diophantus had the complete set. But of course, the hard part is often not finding the rational points themselves, but proving that the solution set you have is complete. Another example is that I want to show you is this curve due to Alkes and Stoll. And the reason it's interesting is that it has at least 642 rational solutions. And here I've crammed all the x coordinates onto the page, and we don't know if this list is complete. However, in the case of, say, conics, we're pretty good at determining rational points, right? So here's the conic, 2x squared plus 3y squared equals 5. And there's an obvious solution to this if I plug in x equals 1 and y equals 1. And to obtain all the other solutions, x and y, that are rational, this is a pretty classical problem. I draw a line here in green through the rational point I know, and this will hit one other point on the conic, and that other point will be rational if and only if the slope of the line is rational. And in that way, I can sweep through all of the points on the conic, and I get a parameterization of the rational points on the conic. Diophantine equations actually made a comeback on the internet between 2016 and 2019. I think more than 95% of people can't solve this equation here. So we're maybe going shopping for bananas, apples, and pineapples, and our roommate left us this number of bananas, apples, and pineapples to buy. We want positive integer values, of course, for apples, bananas, and pineapples. And if we let A be the number of apples, B be the number of bananas, and C the number of pineapples, we could make a change of variables here and find ourselves with an elliptic curve, which I've written below. It's so if we search in a box, we can find a small point on this elliptic curve. For example, the point minus 100, 260. But this corresponds to fractional and negative values of A, B, and C. So we'll have to work a little bit harder if we want to find positive integer values. But elliptic curves have a group law, right? So in fact, this elliptic curve is rank 1, and it has a little bit of torsion, but P is an infinite order point on this rank 1 curve. So something we can do is we can start adding the point P over and over and see how the values of A, B, and C change. And as we do that, what happens is that 9 times P gives the smallest positive answer. And so there's the values of A, B, and C that, that you would need. And while there are infinitely many rational solutions, A, B, and C, that solve the original question, there will be only finitely many integer solutions, A, B, and C. But unfortunately, this slide is too small to list them all. So like in general, what's going on here? So if I have a nice curve over the rational numbers, the first invariant I might ask about it is its genus. And what we know is that Falting's theorem tells us that if I'm genus at least 2, then I have finitely many rational points, but I don't have an explicit recipe to compute these integer points. And in genus 0 and 1, we have the case of genus 0. It can be infinite if I contain an infinite point, and genus 1, it depends on the Mordell-Weil rank, right? So some corollary of Falting's theorem is that, well, an elliptic curve, so this genus 1 case, can have infinitely many rational points, an affine genus 1 curve has only finitely many integer points. And the motivating question that I have for us today is, if we fix our nice curve of genus at least 2, how can we provably determine the set of rational points? And then that's kind of the motivating question of this whole series, right? But I want to specify a slightly more specific motivating question of the case of a modular curve. And so in the case where X is a modular curve, can we determine the set of rational points from the data of the modular forms associated to our modular curve? So I'd like to move away from taking like an explicit equation for X and determine the rational points from that equation, and then say, if I have a modular curve, is it possible to use some number theoretic information about the modular forms to get our rational points? And of course, the theme of this whole series is to study p-adic methods. And here I'll generally fix p greater than 2 a good prime under the umbrella of Chabati's method. So this particular vein of p-adic methods. And the basic idea of Chabati's method, let's recall, says that our rational points are contained in a finite and computable set of p-adic points, and we hope to compute this set and rule out the non-rational points. So for the first half of my talk, or maybe more, I'm going to start with a test case that leads to the general case. And so I just want to focus on the case of affine elliptic curves of rank 1. And if we can consider the modular form associated to our elliptic curve and use that modular form to determine integer points, or as much information about the integer points on our elliptic curve as we possibly can. Before I get to this specific problem, I'd like to say a couple words about curves over the p-adics, because if you've never thought about curves over the p-adics before, then some things about them can be a little less familiar. So one thing to note about curves over the p-adics is that the p-adic points, or the points over any extension of the p-adics, decompose into open sets called residue disks. And these residue disks are the preimage of an FP point under the reduction map. So there's one residue disk for each FP point of your curve. And if we consider just one residue disk labeled by our FP point P, then since a curve is one-dimensional, then we can always choose a uniformizing parameter for this residue disk. So this thing looks like a copy of ZP, right? It's like a one-dimensional thing. And something very nice about the p-adics is that is the theory of p-adic power series, which is sort of even nicer than the theory of complex power series. So the theorem I have below, it looks kind of technical, but what it's saying is that if I have a power series that converges on ZP, then there's a formula for the number of roots of that power series, just in terms of the coefficients, or the valuation of the coefficients of that p-adic power series. In other words, if I have a power series that converges on ZP, it only has finitely many roots. And that's a key insight about p-adic power series. And how does this apply to curves over the p-adics? Well, something that comes up a lot about curves over the p-adics is, in Chabati, is these locally analytic functions. So a locally analytic function is a function on our curve that on each residue disk of our curve, you can write it as a convergent power series. And a function like this, according to the theorem I just presented to you, has only finitely many zeros. So now we're ready to dive into this quadratic Chabati for elliptic curves of rank 1. So remember that such an elliptic curve of rank 1, if I look at the affine case, then this will have finitely many integer points. And so in the quadratic Chabati theory is going to compute these integer points. And how does it do this? So there's something called a global p-adic height. And what it is, roughly, is it's a symmetric bilinear pairing on my rational points that spits out a QP number, and that's why it's p-adic. But of course, it's also global. So what do I mean by global? Well, roughly, I just mean that it decomposes as a sum of local heights, one for each prime v. There's also another function on my elliptic curve, the p-adic logarithm. You might be familiar with this from Silverman, or like this, it can also be thought of as a Coleman integral. And the interesting thing about these two functions is that they have a relationship between each other. In particular, when E is rank 1, it only has a one-dimensional space of quadratic forms. And so that implies that there's some constant, some QP number, such that the quadratic form H is proportional to the quadratic form log squared for all rational points Z. So there's some gamma such that H of Z equals gamma log squared Z for every Z in E of Q. And so now we want to exploit this relationship. So I copied over this sentence here from the previous slide. And I want to break up the left-hand side, the global height, into the decomposition into local heights for each prime V. So local heights, they have kind of a dual nature. There's the local height at P, and then there's the local height like not at P. If I'm at a prime not equal to P, then the local height is kind of like a discrete combinatorial object. So it's 0 if I don't have bad reduction, if I have good reduction at V. And if I have bad reduction at V, then the local height at V takes values in some finite set that's completely determined by the reduction type. So in this case, the Kodaira type of the elliptic curve. And we can set up a lot of notation and sort of describe what those values will be, but it's not like so important. The point is that there's some set of values that the local height at V can take, and we can kind of sum over all the possible values and put that into some notation W. On the flip side, exactly at P, something else happens. The local height at P is a locally analytic function. So it's given on each residue disk by a p-adic power series. And so when we decompose our global height into the sum of local heights, what we see is this following quadratic Chabati theorem. So if we want to solve for the integer points, we can write this global height as a sum of local height at P, local height away from P, and then that's equal to gamma log squared for this specific constant of proportionality gamma. And on the right-hand side, we have this locally analytic function log. On the left-hand side, we have this local analytic function HP. And this W is just some numbers. And so what we're doing is in each residue disk, writing down these p-adic power series and solving this equation. So the question I became interested in is to start like, what is this gamma, or how could we compute this constant gamma that gives us the proportionality between the global height and the log squared? And one way of rephrasing this is also like, if we want to write the global height in terms of a p-adic power series, like how could we like find the exact p-adic number that gives us that p-adic power series? And so like kind of an immediate answer you have is, well, find any point of infinite order in the Mordell-Weil group, and then compute the left-hand side log squared of that point of infinite order, and compute the right-hand side h of this point, and then divide the two numbers. This is like a little unsatisfying. And also one thing you might notice is that the rational points of our elliptic curve actually do have a natural point of infinite order, which is the trace of a Heegner point. So Heegner points are points, I'll call them y sub k, that are attached to imaginary quadratic fields, k. And at this point in my talk, I'll make some assumptions. So in order to have the existence of Heegner points, we need to assume the Heegner hypothesis, so that every prime q dividing the conductor of our elliptic curve splits in our imaginary quadratic field. So that'll put some restrictions on which imaginary quadratic fields we consider. Going forward in this talk, I'll need p to split in k and be coprime to the conductor. And I'll also need the discriminant of k to be odd and less than -3, and that's to construct certain p-adic L functions. And for the simplicity of all this exposition and formulas, I will require that k has class number 1. This is a pretty big assumption, but I need it to write down a lot of formulas. And so then the goal would be to compute the log squared and the height of the trace of a Heegner point on our rank 1 elliptic curve. So I'll just right away give you the main theorem for integral points on affine elliptic curves. So if I have this affine elliptic curve of rank 1 and I take its associated modular form, but let me just consider it over k, the imaginary quadratic field, where I'm going to find my Heegner point, and I fix my Chabati prime p, and I'm going to require that it's ordinary in this case. Then this constant gamma appearing in this quadratic Chabati procedure is equal to the ratio of two p-adic L values times an explicit constant depending only on the modular form f. And so these p-adic L functions are L functions appearing in papers of Perrin-Riou and Bertolini, Darmon, and Prasanna. And of course, this theorem, it's not like just a theorem about a theoretical formula for gamma, but more importantly, and perhaps actually the difficulty in writing down something like this, is the fact that I can give an algorithm to compute the numerator and the denominator of this, and therefore an algorithm to compute gamma explicitly. And the analog of this theorem holds for rational points on higher genus quotients of modular curves in the appropriate sense of analog. So the global height in this case of higher genus can be written as a linear combination of logarithm functions, and the coefficients will turn out to be special values of p-adic L functions. And I hope to say more about this later in the talk, depending on how much time I have left after I talk about the elliptic curve case. To start, though, I'd like to say a little bit about Heegner points because they play like a leading role in this story. So overarching, Heegner points are special points on J naught of n, corresponding to CM elliptic curves under this like modular interpretation, and their traces generate the rank 1 part of the Mordell-Weil group of J naught of n. So they're really important and interesting. And to say a little bit about how that construction goes, this Heegner hypothesis about primes dividing n splitting means that n splits as a product of this like frac n bar over k. And so using this fractional ideal n here, or its conjugate, I guess, in the way that I've normalized this, I can construct an elliptic curve, and I can use that elliptic curve to define a point on x naught of n. And actually, this elliptic curve will have Cm by OK, the way that we've constructed it. And embedding by the Abel-Jacobi map with base point infinity, this also gives us a point on J naught of n defined over K. And this is what we call the Heegner point. What Gross and Sagier show, or one thing that Gross and Sagier show, is that for some choice of K, the image of this Heegner point under the modular parameterization generates our elliptic curve up to finite index, our rank 1 elliptic curve. But actually, Heegner points are like much more general than this elliptic curve case, and that's something that is important to mention. So let me say a little bit about the more general story of Heegner points. So if we just consider the Heegner points in J naught of n, so we could consider the vector space, say J naught of n K tensored up with Q bar. There's an action of the Hecke operators on this vector space, so that decomposes our vector space into Hecke eigenspaces. And well, what is a Hecke eigenspace? Well, one way to label a Hecke eigenspace is by the Hecke eigenforms, right? So I'll write these Hecke eigenspaces as being labeled by their eigenforms of weight 2 and level n. And well, yk is this Heegner point in J naught of nk, and I can project it onto any component vf, and the projection of my Heegner point onto some component vf will be called ykf. So this is the like f isotypical component of the Heegner point. And using this notation, we can say more explicitly what Gross and Sagier showed. So what Gross and Sagier show more precisely is a statement about the height of the f isotypical component in relation to a certain special value of an L function. So they show that if I have a new form f of weight 2 and level n, then the Nernst-Tate canonical height of the f isotypical component of our Heegner point is proportional to, so that's what this like equals dot, so it's equal up to some explicit constant to the derivative of the L function of f over k evaluated at 1. So if you're looking for an interesting point on J naught of n, you want to find a point that has non-zero height. And now you know that this is proportional to this derivative of an L function, so the special value of an L function. And so on the right-hand side, you have this like special arithmetic value equal to this height of a point. And what Walsh-Breget's theorem tells you is that when f has analytic rank 1, there's actually infinitely many fields where the right-hand side doesn't vanish. So you have a lot of interesting, what that tells you is that Heegner points sort of generate some part of J naught of n. And to be a little bit more specific about like what exactly the Heegner points are generating, recall that there's some isogeny factor of J naught of n attached to this new form f. Like Schimmer calls it a sub f. And so when this height doesn't vanish, when this Nernst-Tate height of the f isotypical component doesn't vanish, then the image of this trace of the f isotypical component is actually generating this mortal Weil group of AF up to finite index. So that's the precise statement that we got about like Heegner, like, so the slogan is that the Heegner points generate the analytic rank 1 part of the Jacobian, and then where that comes from is a statement about the Nernst-Tate height of the f isotypical components being proportional to these special L values. And in particular, this implies this, and the analytic rank 1 part is the part attached to the new forms with the analytic rank 1. So after Gross and Sagier proved this amazing relationship between L values or special L values and Nernst-Tate heights, there came along many p-adic Gross-Sagier theorems. So these p-adic Gross-Sagier formulas relate p-adic invariance of Heegner points to p-adic analytic quantities, so special values of p-adic L functions now. A p-adic L function is an alpha is something that interpolates special values of classical L functions. So in particular, these ones interpolate classical Rankine L functions. And the first one, the first generalization or p-adic version of Gross-Zagier that came along is sort of a direct analog of the Gross and Zagier formula, and this is due to Perrin-Riaux. And Perrin-Riaux shows that there's some p-adic L function whose derivative in what I'll call the cyclotomic direction, for reasons that I probably don't have time to explain in this talk, is proportional to the p-adic height of our F isotypical component. So it's almost as if I took the Gross-Zagier thing and then just made it into, I put a sub P on everything. So I have a height of a Heegner point on the right side, F isotypical component, and the derivative of a p-adic L function on the left side, and not much has changed except that all the quantities here are p-adic. But there's sort of many years later, there's a theorem of Bertolini, Darmon, and Prasanna, which actually interpolates the same set of Rankine L values, but at different Hecke characters. And they construct what I would call an anti-cyclotomic p-adic L function. And the special value of this one it gives you the logarithm squared of the Heegner point, not the F isotypical component, but the actual Heegner point. And since you just saw these quantities appearing in quadratic Chabati, you see that it's sort of promising to try to string these together and make them work into a Chabati formula in general. So I guess I wanted to do like a quick example. So to show that this does work in practice. So if E is this elliptic curve, say x naught of 43 plus, we can pick some prime number like 11, and then we have to also pick some class number 1 field. So here I've chosen q square root minus 7. And then we have this elliptic curve. We want to compute integral points. And what I've done in some mysterious way is compute for u gamma by computing the special value of Perrin-Riaux's L function over the special value of the Bertolini, Darmon, Prasanna L function. And there's this explicit constant that you haven't seen in all its gory detail yet. And so in order to find rational points, we also need to know something about the places of bad reduction here. And so the places of bad reduction are just 43. And here the Kodaira type ends up being like, it's got a node. This is Kodaira type, I guess, like I1. And this corresponds to having no local height contributions. And so if we simplify this formula, we get that we're just solving for the rational points being inside of when the local height at P is equal to gamma log squared. Okay, well, we computed gamma using our special values of L functions, and then we're just expanding this power series for the local height at P and expanding the power series for log squared. And so then that allows us to obtain these integral points and then these points that don't look integral. And also their conjugates under the hyperelliptic involution. So that's how you might apply this kind of thing in practice. But what's unsatisfying is that I haven't told you like what any of these p-adic L functions are or how you would compute them, I guess. So the major difficulty in proving a theorem like this is actually the anti-cyclotomic p-adic L function of Bertolini, Darmon, and Prasanna. So let me say like what this L function is. So for me, and there's many ways to define this, but for me, the story starts with something called the Shimura-Moss derivative operator. And so I've written it out in terms of the complex numbers. So delta k is like this 1 over 2 pi I times this del z operator plus k over 2 pi y, 2i y. And what this does to a modular form or a nearly holomorphic modular form of weight k is it takes a nearly holomorphic modular form of weight k and it increases the weight by 2. And you can, of course, keep composing it, and we'll write delta to the j as the composition j times. What's really amazing about this derivative operator is that after normalizing by some period, the values of the delta to the j of our new form f, evaluated at a CM point, are actually algebraic. And we have some control over the algebraicity. They belong to the compositum of the CM field of that CM point and the coefficient field of f. Let me show you an example. So here I've picked n equals 83. I've picked this CM point coming from this like root minus 11. This is like a Heegner point for k equals q root minus 11. And I'm going to embed things p-adically, so 3-adically, rather than show you the algebraic point, and that's to make a point about something in a second. And then rather than printing for you the values of just the Shimura-Mas derivative of f like evaluated at the CM point, well, first I'm going to normalize that by the appropriate period, and then I'm also going to square the whole thing and multiply by a certain factor here. It's like an Euler factor. And I've embedded it in Q3. Okay, I hope you'll forgive me for modifying it a little bit, but there's a point to it. So here I've plugged in that formula, r equals 3, r equals 3 squared, and this is r is like how many times I'm applying this derivative operator, -1. And as I do this, you'll notice that the values seem to be like p-adically stabilizing, which suggests that there's some like function of r going on. There's some p-adic function of r. And so what is that function of r? This is the p-adic L function. And so we'll define this p-adic L function, or we'll say that this is equal to this quantity that I was computing for you on the right-hand side. So this is the Bernoulli-Darmon-Prasanna p-adic L function. And unfortunately for us, the special value occurs at a value that's not in the range of interpolation. So if you're not used to thinking about p-adic L functions, when something is in the range of interpolation, we can just plug in a bunch of values, get closer and closer, and then like take a limit. And if I'm not in a value that's in the range of interpolation, it's really unclear what to do. So that's like maybe the hardest part of this whole thing, is that the special value is not like in the range of interpolation. So I can't just take a bunch of classical things to approximate the special value. I have to find a way to get this special value that isn't approximated by classical things in a direct way. However, like there's hope, like we can still recover this value. And so this idea comes from inspiration from a paper of Rubin. And so before I tell you about this, like it does rely on being able to compute in the range of interpolation. So let's say like a couple words about how to compute something in the range of interpolation. Well, to compute any value here, we would need to compute the Shimura-Mas derivative of our function evaluated at a CM point. And so I did show you these values, but how did I actually do this? Well, what happens is that these actually satisfy some recurrence relation due to some large amount of structure on the ring of modular forms for gamma naught of n. And there's some kind of like Fibonacci like iterative relation that allows you to obtain the r+1 value from the r value and the r-1 value. So that's a really interesting thing I recommend looking into, but I don't have enough time to talk about that. So let me just say briefly about outside the range of interpolation. So for brevity, I'm going to call L of r this value at r. So then with this notation, what we want to do is compute L of 0. And that is the special value, so it's proportional to log squared of our Heegner point. And instead, what we'll do is compute a bunch of auxiliary values, L of p-1, L of 2p-1, up to some bound bp-1. And the proposition is that L of 0 raised to the p-1 over 2 power is equal to this kind of weighted sum of auxiliary values mod p to the b. And in this way, we can approximate L of 0, and we can actually recover the correct sign on L of 0 from this congruence here. Okay, so here's a quick example, like proof of concept. here I have 37a1, q square root minus 11, p equals 5. Fun little computation. We compute L of R for like R equals 4, 8, 12, and so on. And applying this proposition, we're able to compute L of 0 squared, mod p to the 10th. And then to get the sign of L of 0, we look at L of 8, and that gives us the special value mod p to the 10th. And so that is telling us about the Heegner point associated to q root minus 11 on this elliptic curve and its logarithm squared. I want to say a couple of words about the height. The height, it turns out, so this is Perrin-Rieux's Piaget-Gross-Zagier theorem. I've just thrown in the special, or the constants here. So her special value of the L function is proportional to the height of the Heegner point times there's a unit root of Frobenius, and there's a degree of a modular parameterization going on. So to compute this L function, you can relate it to an L function that appears in, well, I use this MTT because it appears in a paper of Mazur, Tate, and Teitelbaum. And the reason why you want to relate it back to this other L function due to Mazur, Tate, and Teitelbaum is that this other L function can be computed using overconvergent modular symbols, and that was work of Pollock and Stevens. And then you have left over like a bunch of explicit quantities, which can be computed in, it's not trivial, but it's also not so difficult. There's some analytic methods for computing the rest of the quantities. So the height turns out to be like a much simpler problem, mainly because the value is within the range of interpolation in this case, while the value of the other L function is not a value in the range of interpolation. And so that's the key difference between the two sides. Okay. So the remaining time I have, I'm hoping to say something about higher genus curves, but maybe I'll take a second to see if there are any questions. I haven't seen any questions in the chat, but like, I don't know if anyone has questions before I proceed.
No, I think please go on.
Cool. Okay, so right, so elliptic curves, affine elliptic curves of rank 1 are great, but of course there are better methods for computing integral points on affine elliptic curves. Nobody like sets out to find integral points and then says, I'm going to use quadratic Chabati. And so like the point of that was like kind of a testing ground, or like the simplest possible case to develop a theory in. And then of course the goal is to set out to do some higher genus examples. And so suppose we have some curve of genus at least 2, let's call it Jacobian J of X, then the question becomes like, can we extend the previous methods to compute the rational points on our curve? There's a little more notation that has to be set up here. So like we saw in Alex's talk and Jen's talk, we have to fix some correspondence or endomorphism of our Jacobian. So I have this Z in the kernel of Narayan-Zaveri of J to Narayan-Zaveri of X. And using this correspondence along with a rational base point, which I've just suppressed from my notation, I apologize, then we can define a height on the rational points of X via sort of this Nekovar theory of p-adic heights and Galois representations. And it's not too important that you know how we do that, luckily, as I'm only kind of giving a sketch of this. And again, this is like a global height. And so we also get local heights, HV, which are defined on the QV points of our curve. So the global height does also decompose into HP and HV, where the sum is over V not equal to P. And again, we have this duality like we had in the elliptic curve case, where this height HP is a locally analytic function, so it's given by a power series on each residue disk, and the local heights away from P have finite image. So in particular, when V is a prime of good reduction, it's just equal to 0. And when V is a prime of bad reduction, the image of these is determined by the reduction type and the combinatorics of the reduction type, and it will have like finitely many values. But the combinatorics of that becomes much harder and is in general quite difficult problem. Unlike in the elliptic curve case where you can do it just from the Kodaira types, the classification of Kodaira types for higher genus is just like not really well established. Okay, so now we want to like generalize this H equals gamma log squared that we had and so the general analog of writing H equals gamma log squared, so we're not in a one-dimensional space anymore. And so what we would want to do is write H of Z in terms of a basis of symmetric bilinear pairings on the Jacobian. What does that mean exactly? Well, so if I fix a basis for my differential forms, holomorphic differential forms, let's call them omega 1 through omega g, then I can find a basis of symmetric bilinear forms given by these like products of logarithms with respect to omega I. So like log omega I times log omega j plus log omega, like plus the converse, where here I've swapped the divisors in each one. And I'll call these functions like gij. And then, so when we're applying quadratic Chabati, we usually make this assumption that the rank of the Jacobian, the Mordell-Weil rank, is equal to the genus. And so like suppose that the rank is equal to the genus and we knew some basis for the Mordell-Weil group of our Jacobian. In that case, we could determine some coefficients, we'll call them now like gamma ij, where H of Z is equal to gamma ij times gij, like the sum of this, right? And so this is the general analog, right? Where we want to write H in terms of this basis of symmetric bilinear pairings. But to do that, we would need to know like sufficiently many rational points. And one way to do that is if we knew, say, a basis for the Jacobian, the Mordell-Weil group of the Jacobian, and then we could plug in this basis and do some sort of linear algebra to determine the coefficients. And the reason for doing this is that you want to write your global height as some locally analytic function, and these are your locally analytic functions, this gij. And so in order to express H in terms of a power series, you need to determine these coefficients gamma ij. And just to like go all the way, just to like reiterate why that's so important, you need to do this in order to explicitly find rational points because you're trying to solve like zeros of p-adic power series. So you need to be able to explicitly write down your p-adic power series. Okay, that's our setup. So the theorem I'm going to write down, it works only on some modular curves. So like the case I'm going to consider is when I have this dominant map from x naught of n. So in this case, suppose I have this dominant map and I'm of genus G. In addition, I'm going to suppose my Jacobian is simple. If I'm not simple, maybe there's a way to like sort of do Chabatian products. I think Nathan has some work on this. But so we're going to restrict to this like simple case. So in this like setup, we'll have some associated modular form to our Jacobian of some level M, which is, you know, it has one Galois conjugacy class because we're in the simple Jacobian. And we know that like the L function of this, these Galois conjugate modular forms, the product of them is equal to the L function of the Jacobian. And the particular case that we want to care about is what I will call a simple new gamma naught of n modular curve. So if we satisfy this dominant and simple case, and furthermore, F is like a new form of level n. So we're requiring that the level actually be n, and that j of x lies in the new part of the Jacobian. Those are the like additional requirements. So remember that quadratic Chabati also has some assumptions, right? That the rank is equal to the genus, like in practice. I mean, in practice, it would be nice if the rank is equal to genus and the Narron-Severi rank is positive. You need some endomorphism to get going. And so in order, like in this special case, note that if the analytic rank of F is 1, then a simple new gamma naught of n modular curve has already satisfies that the rank is equal to genus and that the rank of Narron-Severi is greater than 1. So then the theorem that I want to present you with is that if I start with one of these quotients of x naught of n, so a simple new gamma naught of n modular curve, and its associated new form has analytic rank 1, let's call its coefficient field EF, and I've collected here all our hypotheses on K, our imaginary quadratic field. So it's class number 1, all discriminant t less than 3, and again, P is our good ordinary prime splitting in K. Then we can write down these coefficients, which are indexed by the Galois group of EF over Q. So gamma sub sigma comes from some explicit constant depending only on F times the degree of phi, our quotient map, times a special value of Perrin-Rieux's L function over special value of this Bertolini-Darmon-Prasanna L function. And these we can again compute. And furthermore, this gives us a way to write the height in terms of the logarithm squared. So it gives us this equality between for the height as a locally analytic function. And this theorem allows us to compute a finite set of p-adic points containing the rational points. So one kind of remark I wanted to make about this is that it allows you to write down a Q expansion of the height on your modular curve. So if I write as alpha the endomorphism associated to my correspondence, since I'm on a modular curve, we can assume that alpha is, say, like a sum of Hecke operators in the identity for simplicity. So like alpha is taking an eigenform and scaling it by some number, like say like some Fourier coefficient or something like that. So the Q expansion of the Neckar height turns out to be this gamma sigma that we saw on the previous page times the integral of the F sigma dq over Q times a certain constant depending on F sigma and Z plus this lambda plus this other integral of F sigma. So it's this quadratic thing here. And what is this constant that we haven't seen yet? Well, this constant actually appears in the literature as the logarithm of a Chow-Heegner point with respect to this base point B. So it's a Chow-Heegner point associated to Z with respect to B. So it's what's going on inside this integrand is like you have this Gross-Kudla-Schoen modified diagonal cycle, and we're projecting it with respect to this endomorphism or this correspondence Z. And so I haven't really explained what any of this is, and I apologize, but I just wanted to like allude to the fact that that as a consequence of this theorem here, what you get is like some very interesting like that the global height has a Q expansion, and all of the terms in the Q expansion can be written down. All the coefficients are products of some very interesting constants, and these constants have interesting modular descriptions. And so just to give you a quick example, so like, I don't know, my favorite genus Q modular curve is x naught is 67 plus. So here, the coefficient field is Q squared of 5, and this is one way of writing Q squared of 5, and I've let P equal 11. And so I'm going to fix this embedding into the 11-adic numbers. And here's the quadratic imaginary field that I've picked for my Heegner point. We can write down the Q expansion from the previous slide. It looks like this. And this comes from base point infinity and the correspondence -4T11. And we can also write down these two gamma F sigmas. They look like this. These CFZs, they look like this. These are the constants coming from this like Chow-Heegner point associated to Z and the base point. And this is just one quick example, but it also works. So this gives us you can use this to find p-adic points containing the rational points, and I've also done some examples with some other small modular curves, but there's some restrictions on the class number which make it hard to generalize this code explicitly. Yeah, so I guess in summary, I wanted to say that like something that like quadratic Chabati is amazing and like it can do so many examples of modular curves. But a dream of mine and of many people's is to like push beyond equations, because it seems like a lot of people have done every possible small equation of modular curves. Although I could be wrong. Like I didn't know that genus 6 was possible with equations. So and so like perhaps like there's like a way to just directly rely on modular forms in their data like more in their quadratic Chabati algorithms. And so I'm interested in methods that they can compute more quadratic Chabati data, more arithmetic data from the modular forms that control the rational points. And so yeah, one example of this are theorems of Gross and Sagier and the p-adic analogs. And yeah, there's just so much more work to be done in this direction. I've seen many people working in this area. So I'm excited to see kind of what else goes in this direction next. So thank you very much for your attention.
Thank you for that wonderful talk. Well, this is a great time for people to ask questions. Would anyone like to start by asking a question?
I had a small question. First of all, thank you very much for the talk. It was really interesting. I don't think I've actually heard you speak about this before, and it's really cool stuff. The thing I was going to ask you, in this example at the end, we have your X0 67 plus. Like your theorem is giving you like this Q expansion, sort of like the Q expansion of your quadratic Chabati function in a neighborhood of infinity, or like the residue disk of infinity. Do you have to do something to like take that away, like pass over to other residue disks in order to compute this set of p-adic points containing the rational points?
Yeah, so the Q expansion doesn't tell you about the other residue disks. It's sort of a fun side effect, and it won't let you solve for the rational points. So it's absolutely a good remark to make. To find the other residue disks, you have to compute power series expansions, and you have to use the equation of the modular curve. Like I don't know a way to get around this right now. So that's where the method breaks down. It's not a completely modular method. So yeah, this Q expansion is a purely like local in one residue disk method. And then to find this set of p-adic points containing the rational points, the only way I know how to do it right now is to use the equation for the curve to compute things like the local height at P and yeah. So.
Okay, thanks. Even still having the Q expansion around that in that one disk is pretty amazing to have that without any equations.
I had a couple of questions. I'm curious how well your algorithm scales. I noticed the examples you mostly give are genus 2, but if I had like a higher genus quotient, and then also how it scales with the level. What if n was in the thousands instead of the hundreds, but I could give you all of the modular forms?
So there's two problems. I mean, the answer is pretty poorly. I just want to be like completely transparent. Like I think a lot of it was built to like as a proof that it's possible and like a theoretical concept, but not so much not so much an industrial size algorithm. So one problem is that it's very slow at computing the anti-cyclotomic L function, the special value of the anticyclotomic L function, because in order to compute the values in the range of interpolation, so we're computing like the Arth-Shimura-Maas derivative evaluated at CM point. We're doing a lot of linear algebra with Q expansions, and that's very slow. But I wonder if there's a better way to do this using similar things to what like Alan Lauder does with like his work on periodic L functions there. And I'm not sure if it's possible to use, instead of Q expansions, something like more that like, yeah, something nicer, I guess. And then the other, so that's where the like scaling with n fails, I think. And then why I only do genus 2 examples is like, so I do have a genus 3 example in my paper, but because I've restricted to class number 1 and I have some like various splitting conditions, sometimes it's actually not possible to find a K that satisfies all the conditions that you need, and that gets harder as the coefficient field grows. And so this is a thing that one like could definitely get rid of, like class number, there's no reason really you need class number 1, but you just, I haven't done the work to remove the hypothesis, but it would be really cool if someone wanted to do that work. So
Yeah, that maybe answers sort of my next question was, yeah, how hard would it be to generalize like to quotients of x1 or yeah.
it's definitely possible, but like I think a careful reading of Perenrio and Bertolini, Darman, Prasanna would be in order, and some like it's not trivial, I would say. Like it would be interesting if someone wanted to work out exactly how to do this.
And maybe one just last final point of clarification, and all the examples you gave, you're actually taking a quotient that's coming from automorphisms on the modular curve, but is that necessary?
I think I did it because I needed the Fricka sign to be a certain thing. Like I needed the rank to equal the genus, and so that was the easiest thing for me to do to guarantee the analytic rank. But I don't think it should be particularly necessary.
Yeah, that's what I would assume. Just wanted to share. Thank you. Great talk.
Yeah, thanks again.